So today's topic is fusion, and just like the topic, I'm fusing a few of these dot points together. I've got dot points from the um, beginning of section 1, from the end of section 1, and from section 4, I think, of this topic. So I'm really going all over the place here. However, fusion is all over the place. And in fact, as you look through the topic, you'll see it crop up again and again. So why does it keep cropping it up? Well, the dot point we're up to, this one, is we're analyzing and applying Einstein's description of the equivalence of energy and mass, which is E equals mc squared, energy and mass, that's M and E, and relating it to the nuclear reactions that occur in stars. These nuclear reactions are nuclear fission, and two examples of those are the proton-proton chain and the CNO cycle. So I thought we may as well just lump all these together, right? If we look at the proton-proton chain, the CNO cycle, and we analyze and apply E equals mc squared to those two situations, we should be in a pretty good state for these three dot points. Applying E equals mc squared to these two things gives us the amount of, gives us the release of energy as well. So we should be good. So what is the proton-proton chain? Let's start with that. So inside the sun, we have this ball of real hot, dense gas. It's hot because it's dense. It's dense because of gravity. Gravity's squeezing it all together, and the more you squeeze a gas, the hotter it gets. So as it's getting squeezed in the core, which is under very high pressure from all the gas of the sun on top of it, plus very high temperatures. So those gas molecules, well, they're not really gas, it's plasma. Those particles, those plasma particles, mostly hydrogen, are whizzing around at high speeds so fast that because of their speed and because a little bit of quantum tunneling, they can collide with each other. So this high pressure in the middle of this sun can cause protons to collide with each other, overcoming their electric repulsion, the positive repulsion, allowing them to fuse to each other, the strong nuclear force taking over. And this is the beginning of the proton-proton chain. So this proton-proton chain starts with two protons crashing into each other. Let's draw that here. Proton and proton crash to form a double proton, except that double proton, one of those protons quickly decays into a neutron, and that releases a positron. Let's just do a positive E, and a neutrino. And a neutrino. There we go. All right, so we have a slightly bigger hydrogen. We don't have helium yet. So what needs to happen is this then collides with another proton, right? Another hydrogen. And what do we get here? Nothing fancy. We just now have a helium-3 nucleus with two protons and a neutron. Now all this has to happen again over here so that we have another helium-3 nucleus. And now those two helium-3 nuclei are colliding to form our helium-4 nucleus, which is nice and stable. Here we go, helium-4, two protons, two neutrons, plus two protons are going to be ejected in that process as well, because of course we have 6 nucleons here, and now we have 6 nucleons down there. The creation of the second one here, just like the first one, it involved 3 protons coming together, 2 initially, and then a third one later on. And of course, one of those protons decayed into a neutron, releasing another positron and a neutrino. Here we go. Okay, so we've got all the bits and pieces. What did we, so where does the energy come from? How does this work? So E equals mc squared says that mass can convert into energy under the right circumstances. The masses we started with here, we started with 6 protons, right? 6 protons. And what did we end up with? We end up with a 2 positrons, 2 neutrinos, 2 protons, and a helium nucleus. Okay, so some of the mass from what we originally had has been lost in this process. And when I say lost, I don't mean it's actually lost. Instead, it's been converted into energy. So some of the mass of the original 6 protons has been converted to energy. So when we add up the masses of the 6 protons, that doesn't equal what we get when we add up the masses of what we had down the bottom here. We can rewrite all of this as a nuclear equation where we started with 6 protons. So that's 6 hydrogen atoms, hydrogen 1, 6 of them, turned into a helium, He, 4, 2, plus 2 protons, that is 2 hydrogen nuclei, plus 2 positrons, that'd be 0 atomic mass and 1 atomic number because they're positive, and plus 2 neutrinos. Now the neutrinos, their mass is negligible. Even the positrons probably have negligible mass, but the neutrinos, we actually don't know their mass. It is not a known number, so we're going to discount them. I've got I had to look up, Google the mass of a helium nucleus. Here it is here. However, the other masses you do not need to be given in the question. This is because the other masses you can find on your data sheet. A helium nucleus is just 1 proton. So if you look at your data sheet, you can see the mass of a proton is here, and a positron is the antiparticle of an electron. An electron is, the mass of an electron is on your data sheet as well. It is here as well. So what we have to do is we have to do 6 times the mass of proton, and we need to compare that to the mass of a helium nucleus plus 2 times the mass of a proton plus 2 times the mass of an electron, ignoring this. The difference should be the difference in mass, or the mass defect. So let's give that a go. So I've got my calculator here, and when I do 6 times the mass of proton, I get a value, let's pick a different color, get a value of 1.0 times 10 to the negative 26. This is in kilograms, of course. And when I try the other side, and I put that in my calculator, I get the same number because my calculator is being dumb. Okay, sorry, had to fix my calculator. When I try the right-hand side, I get 9.99 plus some other decimal places times 10 to the negative 27 kilograms. And I'm going to have to do the left-hand side again. Let me try that. Very close to what I said here, 1.0038. So this is about good enough. Okay, so obviously this number here is slightly bigger than this number here. 9's bigger than 1, but this is to the negative 26, this is the negative 27. So we have lost some mass, this mass defect. This mass, where has it gone? It's actually hidden here all along. All of this on this side plus energy. Sometimes people might say energy in the form of a gamma wave. Okay, how much energy? Well, let's calculate that mass defect. So I take one minus the other, I get a mass defect, which I'm going to write over here. Mass defect of 4.54 decimal places times 10 to the negative 29. So very small amount of mass. However, we need to plug this into our equation, E equals mc squared. We have the mass, which is 4.54 times 10 to the negative 29. We need to times that by c squared. So we get to times it by quite a large number, giving us giving us an energy of 4.09 times 10 to the negative 12 joules of energy. There you go. Okay, calculated. So still a very tiny amount of energy, but keep in mind this is for every time we get 6 protons forming 1 helium. Okay, the sun is huge. Comparing the sun to the Earth shows you just how mind-boggling big it is, and it's losing billions of kilograms of mass in this process every second. So billions of kilograms of mass in chunks this big means you're turning into a lot of you're getting a lot of helium. Okay, let's talk now about the CNO cycle, carbon, nitrogen, oxygen cycle. I'm going to need to clear a bit of space here. Let's clear those off to the side. All that. Okay, now I'm not going to draw this one because it's a little involved. Instead, I found this copy on the internet. Let's bring it in here. So the CNO cycle, this is presuming that we start off with some carbon, nitrogen, or oxygen. That's what CNO stands for. And let's talk about this pretending that we've started with some carbon. This is carbon 12, okay? That means it's got 12 nucleons, 6 protons, 6 neutrons. So you've got some carbon in your sun or in your star, and the star squeezes a hydrogen nucleus into that carbon, okay? So now we've gone from 6 to 7 protons, making it from carbon to nitrogen. And 7 protons and 6 neutrons means it's nitrogen 13. Now nitrogen 13 is unstable, it undergoes beta decay, just like in the previous one, where one of its protons turns into a neutron, emitting a positron, that's this little green guy, and a neutrino. This happened in the previous thing too. Okay, when it does that, still has 13 nucleons, a proton turned into a neutron, so it's still 13, but one of its protons changed. So it had 7 protons, now it has 6, so it's back to being carbon 13. Protons added. When carbon gets a proton, turns into nitrogen. That's what happened here. That's what happens here as well. Except this was carbon 12 going into carbon 13. Now we've got carbon 13 into nitrogen 14. Sorry, I said carbon 4, that's nitrogen. All right, same thing happens again. Nitrogen now becomes oxygen. Nitrogen 14 gains a proton, oxygen 15 gains an atomic mass, 14, 15, and it gains atomic number 7 to 8, which is oxygen. Okay, oxygen 15 is unstable. It's going to undergo beta decay. We get a positron, neutrino, and one of the protons turns into a neutron. Proton turned to a neutron. We had 8. Now we have 7 again. We're back to nitrogen. Here, helium attaches again. We get to nitrogen. We get to fluorine, right? Nitrogen plus another proton means we have fluorine 16. However, this is not stable, and a helium 4 drops off it. So we had 16 losing 4, so it's gone to 12. So we've gone 16 to 12, plus it had it's not fluorine, it's oxygen. Why did I say fluorine? Sorry, it would be oxygen 16. Oxygen 16 loses 4, that's gone down to 12, and oxygen's number 8 lost 2 protons in that helium nucleus, so now it's 6, which is carbon, back to the beginning. So has this done anything? Did we just turn carbon into more carbon? No. What we did is we turned these protons, 1, 2, 3, 4 protons that came in, we turned them into a helium nucleus. If we write out this equation, what we find is we start off with, say, we start off with a carbon 12, 6, plus the 4 hydrogens, and they're turning into a carbon 6, plus a helium nucleus, helium 2, plus we've got our 2 neutrinos here and here. Sorry, those are our 2 positrons and our 2 neutrinos here and here. Okay, so I can add them in as well. Plus 2 positrons, 0, 1, plus 2 neutrinos. Okay, now, not going to do all the maths again because this equation turns out it's exactly the same as the last one, right? There's 2 carbons on both sides, so they're not changing the mass. So if I just get rid of them and we're ignoring the 2 neutrinos, we've got 4 hydrogens on one side, and we've got a helium and 2 positrons on the other. This is actually the same as before. Before we had 6 hydrogens on one side, and the other side we had a helium, 2 positrons, and 2 more hydrogens. So if we cut 2 hydrogens of this, cut 2 off this, becomes 4, and we get exactly the same as this. So how much energy is released? The exact same amount as last time. I've still got it on my calculator, 4.087 times 10 to the negative 12 joules of energy. That's it.